So chapter 4, what we are going to study? We are going to study this concept here, sample space, right? It's a relatively abstract concept. So how do we understand that? We can use this example here. If we are doing some experiment, everybody, if I toss a coin, right, a regular coin, what's the possible outcome I can get, right? I can get either head or tail, right? Usually we are using capital H for head, capital T for tail, right? I put all the possible outcome together and then use that bracket, right? That this outcome here, what do we say? Sample space. That's it, right? If I roll a die, everybody, a dice, right? So how many we have from regular one, right? 1, 2, 3, 4, 5, 6. Have played like those games, right? Monopoly, those dice, right? What's the possible outcome, right? If you roll one dice here, one possible outcome you have 1, 2, 3, 4, 5, 6. You put them together, that is what we say space. That's easy, right? Now, if I'm asking a question, right? Yes or no question. What's the possible no, right? I put them together. That's it. That's what we call sample space. Okay, now a relatively complex example. What if I toss 2 coins, right? How do I get all possible outcome together, right? So I'm going to introduce this tree diagram. Everybody, tree diagram to help us to cover all possible cases. Okay, so this tree diagram is very, very useful. So after we toss 2 coins, right? So what's the possible outcome for the first coin? Could it be a head or tail, right? And then if the first coin is head, right? The second coin could be head or tail. So in that case, we can read the possible outcome directly. Is that right? So you can see that here we have, right? It's like head, head. That's the read it from the output directly, right? Second one here, head, tail, tail, head, tail, tail. So altogether, how many output here we have? 4, right? We'll put them together. That's what we say, sample space. Okay, so this is a very useful way to list all the possible situations. If you don't do this way, you may miss certain situation. Like this example, a little bit more complex example here. Say we want to study the sample space for all the possible gender of a 3 children case here, right? So we have, say, the first child, right, could be a boy or girl, right? So if the first child is girl, the second one could be a boy or girl, right? Continue based on each case here. If the first one is girl, second one is girl, the third one could be a boy or girl, right? So we can read this directly for our output here. So it's girl, girl, girl. That's one output. Similarly, girl, girl, boy, second, right? So we can read this all of them, right? You will not miss any of that. But if you don't do this one, if you don't use the tree diagram, everybody, like you can try this by yourself, try to write down all the possible cases for the gender, right? Most likely you will miss like some cases. Altogether, we see there are 8 possible outcomes. So that's a sample space we are getting. Everybody, you may wonder, why do we study that, right? Why do we, spend so much energy writing down all possible outcome here, right? Why we are doing this? The motivation is that once you have those all possible outcomes, It will be very easy, straightforward, help you calculate those probability questions. Remember, one of the most popular questions for our class is calculate probability. Like this example here. What's the probability for us to get this combination output, right? You have 2 girls, 1 boy, right? So you have the 3 children case here, right? What's the possibility that you will get that combination with 2 girls, 1 boy? So remember, everybody, in the future, right? We studied stats, we studied probability. Whenever we see that question in terms of probability, remind you something fundamental. So what's that? That is, whenever you think about probability, that means what? That means something divided by something. Everybody? I want this one you have that in your mind so you don't get lost. Where do you start? Right? So probability is always something divided by something. The denominator here is the total possible case you are getting. All possible number of cases that you are getting, right? Numerator is number of cases that we are asking in the consideration. So in this case here, we are asking, what's the probability for us to get this combination output have 2 girls, 1 boy, right? So probability is something divided by something. Denominator is total possible cases. So previously, we just write down all possible cases. How many? 8, right? So the denominator is 8, right? Now, how about the numerator? The numerator here, we are talking about something that we are asking, right? How many cases in the output here we have, everybody, we have 2 girls, 1 boy, right? So it's 1 case, is right? And then another case, this is not, that's 1, right? So 3 cases, all the other here, they have more than 2 boys, right? So how many cases that we are asking? 3. So what's the answer? Our answer is 3 out of 8. That's the probability we are able to get this outcome here. So hopefully that's clear why we are doing the calculation, right? How do we do the probability calculation based on output coming from the sample space? With all those information here, right, it's very easy, straightforward, right? Simply count. Everybody, that's the probability, okay? So we put 1 note here that is, whenever you see anything, right, for any event, everybody, for any event, right, the corresponding probability for any event, right, always between 0 and 1, right? So if you hear someone that is saying probability of raining tomorrow is 150% tomorrow, right? Right. That means that person did not study statistics, right? Whenever we talk about probability, always between 0 and 1, right? If you hear someone say probability of something is 1.5, 1.2, negative 2.3, right? Something's not right, right? Negative 0.5, no way. We cannot get a negative. Okay, so hopefully that's you got this idea of the probability. Okay, now second part we want to cover is what we call this complementary event. Everybody, complementary event. So using human being language, right? That means opposite event. Opposite event. We are going to use some example here to help you explain what's the opposite meaning, right? So before we go that, I want to introduce this Venn diagram. It's a very useful technique that, you will see that in mathematics class, in stats class, in computer science class, Venn diagram. So this square here is to cover everything, like all the possible situations. Like back to our previous example, like all the possible outcome for like 3 children, the gender, right? All possible 8 cases. That's cover all the 8 situations outcome here in that square, right? So for that particular event, E, so say that's the case we want to get 2 girl, 1 boy, right? That combination output, right? So we are using like kind of a circle for that, right? Now, what's the outside, right? Outside, we have 5 cases, right? So they are not belonging to the same category, 2 girls, 1 boy, or the other cases. So we are using this notation here, everybody, E bar. So this is the second time you see that we are using the bar here, right? The first time you see the bar is for the average, the sample average. This time here we have the event, capital E for event, right? And then E bar to indicate the opposite of that event, right? So you see that event E plus the opposite event, that should cover all those 8 cases, remember, right? So that's what we say, like when you add all the probability together, should be equal to what? 100%, should be equal to 1. Okay, so let's use some example here to help you understand better, like how do we use that formula to do the calculation. Say we have 50 people, everybody, right? So out of those 50 people, we know their blood type. Okay, out of those 50 people, we have 21 people. They have a blood type O. Everybody, if you can type in the message window, what is your blood type? Okay, if it's unknown, you can put unknown in the message window, right? And then how many people got type A? We have 22 people. 5 people got a type B. 2 people got type AB, right? So that's altogether give us how many total? That's 50 total, right? So those information they are given here, right? They give you the information about those 50 people, right? Now, what's the question here is you are going to randomly select 1 person out of these 50 people. And I'm going to ask you that what's the probability of that person to get the type O, right? So you randomly select 1 person out of that 50 people, right? So hopefully that question is clear. I mean, it's a relatively straightforward question, right? And you randomly select 1 person out of these 50 people. You want to ask, what's the probability for that person to be get a type O here? Remember, probability is what? Is something divided by something. It's a ratio, is right? Denominator is all the possible cases we have, right? So we select 1 person out of the 50 people, how many cases we can get? 50, right? 50 choice, that's easy, straightforward. Now, in the numerator is number of cases that we are asking. We are asking that person we are get a type O. So how many people here we have type O here? 21, right? So 21 divided by 50. Everybody? That's straightforward, right? All right, question number 2. Same, you randomly select 1 person, right? Out of these 50 people, we're asking the probability of that person get either A or B. So probability is something divided by something, right? Select 1 person out of 50 people, denominator 50 choice. In the numerator, you can get either A, how many people here we have A, 22. How many people we got B here? 5, right? So they are saying either A or B, right? So we add them together, 27 divided by 50. That's the corresponding probability. So some people was asking, like, do we need to get the decimals, right, or not, right? So I would say, depending on the question, right? Usually, like so far from the homework question, what we are usually given is a multiple choice, right? So you compare to the answer you have. If it's a fraction, right, something divided by something, simply compare that, right? If it's a decimal, that means you do have to convert this fraction here to the decimal and find out which one is more close. Everybody? Sometimes, especially for statistics, right? Most of the time, ideally, we don't have it exactly match, right? But as long as you can get the answer that is the most close one, that should be okay. So that's for this question here, the probability of getting either A or B. Now, everybody, question number 3. How do we find out the probability of that person, right? This is a little bit difficult for me to pronounce this word here, right? Neither. I try my best to pronounce this one.
Neither.
Thank you, right? English is difficult for me. To me, I understand this as not A, not B. Okay, so that means what? That means could it be type O or could it be type AB, right? So if I do the calculation, everybody, I'm going to erase that. So that's going to be something divided by something. Denominator is all the possible cases we got 50, right? In the numerator is number of cases we are asking. We are asking not A, not B. That means either this 21 or 2. So add them together, 23, right? Divided by 50. That's one way, right? That's one way. There's another way you can consider that is, let me see, because they are asking not A, not B, right? So you think about the opposite event, everybody. That's what we just learned. We call this complementary event, the EBA, right? The complementary event will be what? Will be A or B. Actually, will be what we are getting from this question here. Think about that. Is that right? So you have 2 events, right? So I can write it down. Let me see. Like this is the event. Right. Right. This is the event. So this is the event that getting either A or B, right? What is the opposite? The complementary event, E bar. That's what we have this one here, right? So not A, not B. Remember the formula we just introduced. This one here, everybody, right? This one, when we add all those 2 probability together, that should be equal to 1, right? So what does that mean? That means if we, right, so we are trying to calculate the probability of E bar, right? Trying to calculate that, E bar, right? We know that one plus the probability of event itself here, right? Should be equal to what? Should be equal to 1, right? Now we know what this probability of that event we got here is what? 27 divided by 50. Right? So you plug this number into this equation here. How do you find out this number here? It's 1 minus this number here, 27 over 50. What you are getting? Exactly 23 over 50. So hopefully it's clear, everybody. Either way is fine, right? It's totally up to you which way you feel comfortable, right, to work on that. You can either work on the straightforward or go in the 1 minus, right? And we will have more examples to cover that, okay? Question number 4. we're asking the probability of not getting type AB, right? So probability of not getting type AB, you think about, there are two ways we can do that, right? Not getting type AB, that means what? That means either A, B, or O, right? So you add 21 plus 22 plus 5, right? Divided by 50. That's what? That's 48 divided by 50. Is that clear? Right? So that's the one way you can do that directly, adding all the possible situation in the numerator, right? Numerator, that's the number of cases we are asking. We are asking the number of cases, not AB, not this one, right? Not that one. So it's the previous three situations. You add them together, 48 divided by total number of cases, 50. That's one way, right? Another way here is using the complementary event. Everybody remember? Say, there's one event here, we say that is the like probability of that event, say getting AB, right? So E is equal to that, that event here, getting, get it the type AB, right? And then we're asking ourselves, what's the E bar, right? I'm going to erase that. I don't want you to get confused. This is the E here. Is the probability of getting AB, right? What's the E bar? E bar is the probability of not getting AB, right? Remember, they have that relationship. When we add those two probabilities together, they should be equal to 1. Right? So here we are trying to find out what's the probability of not getting AB, right? Probability of not getting AB. So it's like a probability of E bar, right? Is equal to 1 minus the corresponding probability of getting AB, right? So 1 minus, what's the probability of getting AB, right? When you randomly select one person out of these 50 people, right? How many people for AB? Only 2 people, right? 2 over 50. Everybody? Hope that's clear. I mean, the calculation here is pretty straightforward, right? So far, we don't have fancy formula yet, okay? So far, I would say the calculation part, it is still pretty straightforward. Now, third section here, we are covering law of large numbers. What is that? If you are reading the textbook, right, they cover this concept like using like 2, 3, 4 pages to explain that concept. I'm trying to use some simple, easy example to explain that. What's the essential idea for this law of large numbers? Everybody, if you have a symmetric coin, okay, symmetric coin, that means what? You have 50% getting head, 50% getting tail, okay? Now, we know ideally like it's half and half, right? 50% head, 50% tail, right? Now, if you toss that coin 10 times, everybody, can you guarantee to get like 5 head, 5 tail? No, I don't think we can guarantee that, right? So, I mean, not only in the, 5-5 breakout, right? I mean, even though I can lose the condition further, say, can you guarantee you toss the coin 10 times, can you guarantee you get the number of heads, like either 4 number of heads or 5 number of heads or 6 number of heads? Can you guarantee that? No, we cannot guarantee that either, right? You see, I mean, sometimes we may get, I toss the coin 10 times, I may get 3 heads, right? Which is possible. I cannot guarantee I can get exactly 5 or exactly 4, exactly 6. Or I cannot guarantee between 4 and 6, right? However, if you toss the coin more number of times, everybody, if you toss the coin 1,000 times, I'm asking the probability for us to get between 400 to 600 number of heads will be much higher than the previous one, right? Now, what if I keep doing that? I toss the coin 1 million times, everybody. My finger will be easily broken, right? So In that case, I'm asking the probability for me to get between 0.4 million to 0.6 million number of heads. Everybody? I would say it's almost for sure, right? After I toss 1 million times of that coin, right? Ideally, it's like 50-50 breakout, right? So it's almost for sure. So you see, out of these 3 experiments here, what's happening? What's the difference? Is that right? The difference is the sample size, everybody, the sample size. When we are getting bigger and bigger, the sample size, we are getting more and more close to the truth, to the fact. So this example here, what's the truth? The fact here is for the symmetric coin, right? Ideally, we should get 50% of head, 50% of tail, right? We cannot guarantee that if I toss the coin relatively few times, so like 10 times or 100,000 times, right? But if you toss the coin more and more times, you will see the output here will be more and more close to the truth, which is close to the half and half, 0.5 million. So that's the essential idea for this law of large numbers, everybody. So instead of using that, reading the textbook, right? That simple, easy example here, as long as you understand that, we are good.